Who is the technical person? No, he's shaking his head.
Oh, it's just me.
You can sit up here.
Thank you, Robert. Sorry for interrupting you. So if I don't know
I can't stand near the mic.
That food died down just now.
third try on it. If I don't know the bandwidth was going to be so good, I would have lobbied for a different time slot. So this is joint work with Blaine. In fact, it's been a long time since it wasn't joint work. In the area we really worked in a few years ago. We didn't even know we were working in the area. So I want to talk about nonlinear equations. They're degenerate, but there's a ellipticity the whole thing. Our initial interest is trying to emulate for other calibrations some of the theory of Subharmonic functions that you can think of as corresponding to the scalar calibration. There's lots of really nice results in several complex variables, and so one of our goals all along the calibration theory was to try to examine the geometry of the calibration. This is maybe examining the analytical side of the calibration. My correspondent queries over my function. So on the geometric side, we looked a lot. Seems to work really well or not at all. So these submanifolds, those are the geometric objects associated with calibration. Query subharmonic functions, whatever that's going to mean, are the analytical objects.
Do you recall what a calibration is?
What a calibration is? It's a differential form on a Riemannian manifold that is declosed and has comass less or equal to 1, which means that the suit over the simple decomposable unit P vectors is no greater than 1, less or equal to 1. The way to think about it is really focus right away on this P submanifolds. It's a condition on their tangent space. So each tangent space of a manifold, you can think of it as a unit P vector, where you pick an orthonormal basis, measure together, and that's the unit P vector, and then the calibration restricts infinitesimally to that tangent space. It's just a linear area between the upper limit of P and lower P forms of P vector. So you want that to be always less or equal to 1, so the calibration at each point determines a hyperplane in the dual space of P vectors. And that hyperplane is, and you set it equal to 1, that's the hyperplane, not 0. You set the linear function equal to 1, then the Grassmannian oriented P plane sits on one side, and the P planes that happen to touch that hyperplane, those are the good P planes, the ones that are calibrated. And the manifold always has a tangent in this good set. If I push, oh wait, okay. So So we were actually pretty successful. But it became clear that we weren't using much about calibration, because that was a little disappointing. So briefly what we did is it was this operator, we look at this, the analog of the conjugate differential in several complex variables, where the phi is a Taylor form. So once we had this analog of the IDD bar operator, then you can ask that it be positive on these preferred. G phi is the G phi is this contact set I was talking about, the P planes that are the good ones that are picked out by the calibration. So go ahead and memorize this. Actually, you can strike out the hypothesis that use parallel. You can so it's pretty general. If you take one of these new kinds of P plurisimple and you take a P submanifold, and the restriction will be classically Laplacian subharmonic. Because of the nature of the lecture, I'll always say classical Laplacian, so you'll figure out why in a minute. It's kind of redundant, but so the proof, this part, I guess, is a little bit of a trick. Not too hard. It may be new in algebra. Where's this? Well, anyway, here's the proof. Put these two things together. On minimal submanifold, the trace of the ambient Hessian is the same as the trace of the Riemannian Hessian on the submanifold. And so you can end up with so now, where we figured out you don't really need a calibration, just take any closed subset of the Gaussian. It doesn't have to be one of these contact sets of the hyperplane. And then define G plurisimple to be the trace of the second derivative. I don't know where should be positive where you take the trace over all these good planes. In other words, restrict the quadratic form of the second derivative, restrict it to W and take the trace. That's what this means. So the same theorem works. Well, not quite the same. Now, since you don't have a calibration, a G submanifold, in other words, a submanifold where the tangent planes are all in this special set G, it's no longer minimal. If they're calibrated, you get the minimality free. So here you just hypothesize it's minimal. G submanifolds, minimal G submanifolds, play the role of the calibration type. And so it's pretty much the same proof, except, well, not quite the same, because harder half the proof got eliminated, so it's easier. And I should mention the converse is true. It's just, all I think of it as two separate theorems. So it's if and only. And the converse only requires that every infinitesimal, in more general geometry, requires that every infinitesimal good plane actually has a submanifold that has that good plane. And then this whole mess is sort of true. So here we are. We want to understand this definition. Very Subharmonic. So why did I put this slide up? So the reason I'm showing you this slide is to make you appreciate the fact that I'm not giving a survey. These are papers Blaine I've written since on this subject. That's supposed to be a joke. Bad joke. Okay, so here's kind of an outline of what I am going to talk about. So I'm going to, except maybe at the end, I'm going to limit to special case, still tons of examples. interesting, they're nevertheless very elementary, of constant coefficient equations and pure second order. But a lot of what I'm going to say will hold for any sub-equation. I'll say maybe more about it. So first we got to have some definitions so something makes sense. And then some elementary properties of these new kinds of subharmonics. And then ask some questions, elementary questions like, what is it about the nonlinear equation that makes the maximum principle true? Sometimes it'll be true, sometimes it won't. And then a very important example. And then another question, and a strong maximum principle hold. And then finally, so this is three subharmonics, but as you probably are familiar as I am, with for example, the Monge-Ampere homogeneous Monge-Ampere equation, you have solutions for harmonics as well. So we need to know what an equation is. And then there's a very basic object here, the dual sub-equation I'm talking about. And monotonicity is an important topic. Let's talk about the Dirichlet problem. So you have to have boundary convexity in a several complex variable case. This would be just a strictly pseudo-convex boundary. But I wouldn't have enough time, so I'm going to say that. And then talk about the Dirichlet problem and when we solve the Dirichlet problem. And then two final topics that have to do with manifolds, or a whole group. And well, the second one, there's almost everywhere there holds in for a complete generality. So let's start with the definition. So it's sort of clear what we want. So let's pick a closed subset. We just make it closed because we want limiting processes to work. So we're trying for sort of minimalistic axiom. So just any closed subset of, this is the space quadratic forms on R. This is where the second derivative is an object in terms of smooth function. So we just want to require the second derivative belong to the set. And that's what I mean by pure second order. The first derivatives don't enter in, and the condition F on the second derivative doesn't depend on X. That's what constant coefficients. Okay, so kind of like distribution theory, except there's a totally different kind of test function. It's just a smooth function that's greater than or equal to the, this is the space of, just like in the several complex variable theory, you want upper semi-continuous functions. They're allowed to take on the value of minus infinity, but not plus infinity. Just like everybody knows all of quantum series. So minus infinity is allowed. So U is less than equal to P in a small neighborhood, and then it equals to X. So now you can take the derivative of the smooth, and you require that it satisfy the condition. And now, I call that F subharmonic. So that's why I said Laplacian subharmonic. Before, we're going to have a million different kinds of subharmonic, depending on whatever, which F is. And some of the notions don't really deserve, we can call them F pluri subharmonic, but there are lots of examples where pluri is not the right word. So let's look at the space of F subharmonic functions, F of X.
F takes the place of pluri.
F takes the place, well, actually, in the several complex variable case, you might ask, what is the F?
Complex lines.
Well, that was on the previous slide. That's where you get the F. But if we want to just say the F, what the F is as a set in here, it's the following. You take the second derivative of the function. So now you just have a real quadratic form on R2, and you take its complex Hermitian part and and you require that that complex Hermitian part be greater than or equal to 0 as a Hermitian complex n by n matrix. So and later on, I'll probably call that P, script PC or something. But that's the F in the classical subharmonic. And that same set then is a fact that that set agrees if you take the cross-bonding of complex quantities, complex bonds in real G2 RP. But all the examples are, I call it examples that come from those G's, the geometric examples. So there are lots of examples that come where you just start with the F. So here are some elementary properties. Maximums. What's that?
A bunch of ants are fighting up there.
Oh.
Army of ants, right?
Oh, okay. So let me tell you here. Well, I thought everybody could see this. This was the only thing that's typed. Okay. The maximum property. Take two of these functions. They're upper semi-continuous, but they're F subharmonic. And then take the maximum of the two. That's F subharmonic. The coherence property. If the function happened to be twice differentiable at a point, then this, I should have written the second derivative there. Gee, that's the full derivative, the full 2j. But read it, second derivative is in the F. Obviously, I didn't read it because it's full more general stuff. It's just white painted out something. Like the X on the F. And so the decreasing sequence property, if you have a decreasing, just like in classical potential theory, a decreasing sequence of subharmonics is always subharmonic. Maybe identically minus infinity, but that's no problem. That's a nice subharmonic function. Well, maybe not nice, but it is a subharmonic. And the uniform limit property, if you have the uniform limit of these subharmonics, then it's subharmonic. And then here's the one that's really important for the Perron process. If you have any family, this thing works some of the time. Can everyone hear me okay?
Exactly.
If you have any family of subharmonic whatsoever, then as long as they're locally uniformly bounded above, then you look at the suit of the family, and it may not be upper semi-continuous. But you just take the upper semi-continuous regularization. And that's always subharmonic. So all these facts hold, so this looks pretty good. But there's, again, kind of a disturbing thing going on here. Because this is any closed set. And so how can that be any condition on the second derivative, and you're going to have all these nice theorems in theory. So it's really too good to be true, but we couldn't find any mistakes. So here's the explanation. If you take a smooth function, you would like, if its second derivative lies in the F, then you'd like it to be F subharmonic. But it might not be, because if you can always take u to be your test function. But that'll set to be greater than equal to u in the neighborhood and equal as a point for it. But so will adding on a quadratic to a quadratic. That's another test function where a is non-negative. So when you apply this test function, you not only get the second derivative of the smooth function, but you get plus any a that's greater than equal to 0. And so if your set F didn't have this monotonicity property that if this is in it and this plus the a is in it, then you'd be in trouble. And you'd end up with the empty set. And so that's why the mystery is not a mystery. If you just take any closed set, you're liable to get this empty set. And all those theorems, I'm not going to go back to them, but if you read carefully the way they were worded, they all hold for the empty set. So we better have more than just a closed set. We better have this condition. It's the key condition of positivity, or P is the set of all non-negative symmetric matrices. And I like to think of this as P monotonicity. because more classically, why monotonicity? More classically, if you have, instead of this condition secondary to the set, you have some function and you want this function to be greater than or equal to 0. Some function, say, little f of the second derivative. Then when you add this a to it, you want the little f to get bigger. So that's the word monotonicity. Okay, well, maybe, hopefully it makes a little more sense now. So now we have our actual definition. A closed subset which satisfies this one condition of being positivity or being p monotone. It is a very weak form of ellipticity that's one of the axioms. And so once you have this condition, now you get the theorem that for C2 functions, the usual calculus definition agrees with this goofy definition. So now there are examples that could take up the rest of the lecture, but P itself, of course, is a sub-equation because P is a convex cone, so P plus P is P. So Blaine and I were kind of surprised. We looked at the literature and couldn't find this theorem that convex equals. So one way is easy, another way is partial proof. Now one could argue that this is the most basic of all the examples because of its role in the definition. So convex functions are at the base of all this. So let's see what I'm trying to say here. So the elementary results we had before, they illustrate the power of the viscosity approach to nonlinear problems. So where you run into trouble is with addition. But now, formulating what you mean by addition is no problem because the quadratic forms are vector space. From the set point of view, you can talk about the sum of two sets and sum of two different sets in vector space. But if you have two sub-equations, and here's the sum. Now there's a technical issue with whether it's closed or not. We're not going to worry about that. But then you can ask this question. So you can ask a linear question even though you're in this highly nonlinear setting. And it's an important question. And the answer is actually non-trivial for the philosophy when you formulate subharmonics this way. So here's just kind of an advertising point. If you were to look at the old-fashioned way where you had the function on this quadratic forms, and this is the usual way of describing a differential inequality, and here's another one, then it's not natural or easy to find this function set. It's pretty obvious. So let's contrast this in analysis. You're pretty good.
When you lower your head, it gets louder.
It gets louder when I do this.
Yeah.
I should look up.
Yeah, when you look up,
Like
I
I'm
can't
getting
hear it.
inspiration. Okay.
So don't turn your neck. And don't look up. You'll be all right.
This. Okay, I got it. Makes me remind me. Here. Okay. So it's common in analysis to, after solving a problem, sometimes to pick the right space of what you mean by function. You never mean the logician's function, whatever that is. So distribution theory is a good example. And so why is it big enough? So what I'm trying to say here is that when you pick a space, you got to pick the right one. There's conditions. You don't want to make it too big, but you want to make it big enough. You can take derivatives, so that in some sense distributions are big enough. Take derivatives of anything, diminished functions, measures. But you want it to not be too big. Now, the usual answer why not too big is some kind of regularity. If you have an elliptic equation or something, then get a solution, which is a distribution, then it's going to be actually classical. So that's a major not too big theorem. I want to emphasize this one. screen it. Here we go. Nervous and pushed the button. So U being greater than or equal to 0, U is a distribution, so that makes sense. You just apply it to these zero infinity functions, and if you apply it to one that's non-negative, then you get a non-negative number. So that's what that means. But then it turns out there's no extra objects. So that's what non-big means. It's a classic, if its distribution satisfies the inequality I just said, then it's actually a classical non-negative measure. So this enables you to do more than just examine linear theory using distributions. You can linear inequalities. And so that means you actually, if you have a convex F, you can just make it the intersection of half spaces and require all the linear inequalities. A half space in quadratic forms is the same as a pure second order constant coefficient differential linear thing. So laying out this theorem, it's surprising, things like this weren't in the literature. I don't know exactly why. But this is an old subject. We actually had some correspondence with some of the originators, Yuki and Randall, and first they said, yeah, sure, they knew it. That was in the literature. Turned out not. So this actually holds. You don't need constant coefficients. Stuck that in there. So now some examples. This is called 11.5 because I was afraid to have examples. You got to have examples, but there are just so many. The fear is if I give the wrong impression. If you just give a couple examples, then you might not realize that that's like the tip of the iceberg. So anyway, here's a couple of examples. So just look at the eigen values of the lambda 1 and lambda 2 are just the first and second eigenvalues here. And so now, this positivity condition says that if this is supposed to be the set F here. The positivity condition says that if you're in the set F and you go vertical, you stay in the set. If you're in the set F and you go horizontal to the right, you're stay in the set. So that's going to be R plus cross, I don't know why that's a plus, cross R plus monotone. In other words, you add any vector that has both components non-negative and you stay in F. That's what the positivity is. Well, that condition says something about the boundary of F, later called E. I don't know. So this boundary has to end up being a graph of a company. And so any such set is going to be a subequation. So you can see there are lots of them. And some of them that you like, but there's a lot of them. You can find one you like. Here's one like the special Lagrange subequation. This one satisfies the positivity, and if U satisfies this one and the C is the right number, then the gradient of U is the special Lagrange submanifold. And it's interesting from the PDE point of view because it doesn't have to be a convex one. The classical PDE point of view covers convex things a lot better than non-convex. Because convex things relate to the linear theory. And it's not what's called uniformly elliptic either. Here's another example that if you look at the Dirichlet problem for this one, it's kind of intriguing. Where a horizontal vertical convexity, this is not the eigenvalues anymore, just either the first X. You get convex horizontally or convex vertically. So think of a disk and the Dirichlet problem. You prescribe a continuous function on the boundary, you try to achieve the solution. Okay, so now to some questions. Now we have the definitions and a few examples. So one of the more elementary questions is, for which subequations F does the maximum principal hold? So what does that mean, the maximum principal? It means pick any compact set, and then the soup on the boundary is bigger than the soup on the whole, in the inside. Now, if you look at the functions that satisfy the maximum principal, there's not going to be a sub-equation that governs those functions because you can't describe those functions with a local property. So here's an example. If you pick any point here, then locally this function does satisfy, meaning if you pick a small compact set about the point, then it satisfies the maximum principal. But if you pick instead a big compact set that starts here and goes over here, then the maximum principal fails. So it's not local. So now we're going to try to answer this question, but first we're going to turn to an example. The subaffine function. So this is, look at the note first, maybe. No, where did I? Oh, here. Forgot to draw attention to this. So these functions aren't going to satisfy a sub-equation, but if they satisfy the maximum principal, that can be reinterpreted by just saying they're sub. Now put quotes around it when I mean honestly sub something. So these are sub the constants. So you pick any constant, and if u is less or equal to the constant on the boundary, then it's less or equal to that constant on the k. That's equivalent to this. So I'll tell you what I mean by quote sub, unquote, the constants. And these guys are sub the constants. Okay. So now we go over here, and we get a bigger class of functions. We want to be sub the affine functions. So these are just constants plus a linear term. So you're supposed to know what sub the affine means. Oh, I wrote it down. Okay. And now, if you're sub the affine, of course you're sub the constants, so the maximum principal will hold. So sub-affine, these are local, and they do satisfy sub-equation. Here's the sub-equation. You'll see why I call it twiddle later. So this is where you've got at least one eigenvalue of the second derivative, non-negative. So you prove that's a sub-equation, and then you have this condition. So it's local. So being sub-affine is a local. So now here's a nice theorem. The proof is kind of elementary, but we were encouraged by the fact that it's sort of clean. And a lot of the nonlinear theory, you have to list a half a page of conditions on which equation you're looking at. If you're going to have results about that include more than one equation. You know, the other option is you just study one equation. So the maximum principal holds for f if and only if f is contained in this set. And let me see, I think I did it later, but let me just. Give these simple eigenvalue picture with just two eigenvalues, where the non-negative, the script p is just this positive quadrant. And this p twiddle guy is everything but the open negative quadrant. So if your f is a subset of what I just shaded, that's if and only if you have the maximum. So this p twiddle is sort of universal. And a good way to compute it is you just, because of the positivity, you just need to look and see is the origin in the interior. If the origin is in the interior, of course the maximum principal will fail. You just pick a point. Well, take any function. Let's see. Oh, so I'm just rephrasing it here. I like this universal way of saying it. So it fails if and only if this guy is a counterexample. So there's a universal counterexample. So it fails if and only if that function I wrote down there is second derivative. There it is. So it fails if and only if this point is not And that's easy to connect all the dots here. So we waited a while, but just recently we looked at this next question, which is a little harder. When is the strong maximum principal hold? So the strong maximum principle says that if you have an interior maximum point, then the function should be a constant. And so if 0 is in the interior, the maximum principle fails, so it's a strong maximum principle. And it's not that hard to show that if 0 is not in the whole set, in other words, 0 is important here. If you're missing 0, then you can prove the strong maximum principle. Like the Long-Ampere determinant equal 1. You get everything below the hyperbola. Lambda 1, lambda 2 equals 1. So the borderline case is the infinite case, where the origin is in the boundary. So let's recall the formula for the second derivative of a radial function. Here it is. So there are only two things that matter. The first derivative.
I got a little lost. Why is that thing two-dimensional over there?
Because it's an example.
So you're speaking very generally.
Yes. Yeah, I just wanted.
So how do I fit these two statements together? Example is very general. Just lost.
Okay, so this picture here illustrates this theorem in the two-dimensional case.
Okay.
And it gives you some feel for, in case you didn't automatically know why F being in here is equivalent to 0 not being in here. If you figure it out for this picture, then the general case. But the picture doesn't have anything to do with the strong maximum. So here we've got this classical formula, but maybe expressed a little different. Usually is in terms of these quadratics here, projection onto the line through x and projection onto the hyperplane perpendicular to x. So the second derivative enters as one coefficient, but the first derivative enters whatever you divide by x. So motivated by that formula, you can look at the radial slice. In other words, pick a direction E, and then look at linear combinations of these two projections, and look at what you get in F. And so here's a picture. Now this is the general case, but the picture's two-dimensional. And again, you have this positivity, just like earlier, where positivity, you can go up this way or you can go this way. So that means that there's, here I wrote down more explicitly, I kind of hinted at it before. Whenever you have this R plus cross R plus monotonicity, then you can, there's a canonical function that gives you the set. So you've got this function, and it could be minus infinity value. It's non-decreasing though. That's what corresponds to this monotonicity. And so this set here, this is the set we're looking at to the right and above the graph of minus F. It's convenient to do it this way, graph minus F, and then write that. So this is the set we want to look at, and then the same F, the A, where is it here? A is, now take A, the second derivative of the radial function psi, and then take lambda, the first derivative divided by the length, and that's what I did here. There's the F of lambda. So this equation translates into the one variable radial subequation for the function psi that makes psi of norm x be a subharmonic. And that's all easy for the infinity functions. It's a little harder. We proved it in general. I didn't write that down. Okay, but here's the answer for the strong maximum principle. Take this canonical function f. We're in the borderline case. So that means f of 0 has to be 0. And and the F has to, the minus F has to decrease, the F increase. So this F is a positive function, and so you just look at, see if that interval is infinite, that's the good case. So I'm going to end up not having enough time, so sorry, I was going to say a little more about that. Okay, so.
Say something why that, what makes that divergence condition relevant?
Yeah, but that's what I was, so what is an equation? That's one more. I mean, some equations are interesting. Actually, there was a long time in several complex variables was a sub-equation. The Fourier subharmonics were considered interesting, and nobody ever considered the, I might have to be the harmonics or the equation, because that's the complex homogeneous long-term pair equation. It's not really a part of the classical Fourier subharmonic theory. First paper that got into that was a paper by Bremen, which I have a date on later. Okay, well anyway, what is an equation? It's going to be the boundary. So I mean that's obvious if you think of what I've done. We've taken a function f of the second derivative, we set it greater than equal to 0, and setting it equal to 0. The equation is just the boundary. So hopefully that's okay. And in fact, the equation uniquely determines the sub-equation. So here's what we want for the equation or for solutions. And so now, this boundary is the intersection of the original set with the complement of the interior. So but this is not a sub-equation. Don't worry, you just have two conditions. But when you take minus it is a sub-equation. And we call it the dual sub-equation. So for every sub-equation there's this dual, it's also a sub-equation. And if it weren't for the minus sign, then you'd be able to talk about upper semi-continuous functions whose second derivative is on the boundary. Okay, so that's why I call this p-twiddle the dual. Okay. So the dual, guys, has all these properties. It's a real duality. You take the dual twice and you're back where you started. And then if you start with the second line there, f is not necessarily a sub-equation, any closed set, then it'll satisfy the positivity, if and only if the dual does. So things seem to stay relatively pretty. And duality reverses the containment. So what is f? Now we can define the solution, or f harmonic, because we want u to have its second derivatives in f, and we want minus u to have its second derivatives in f twiddle, or what's this? If u is smooth, what's the same thing as that? U have its second derivatives in the complement. Sure. So okay, we've got another definition, and now this dual thing has a algebra associated with it, which is kind of the key to a lot. Slide on it here, but I don't have time. I'm going to skip over this. So this little triviality here is the key to these other things. So I won't have time for all of them. I'm just going to generalize where m is no longer script p. And if you have monotonicity with a bigger set, m, then you get, look at this condition. It's always true that if you add something that's f subharmonic with something v that's dually subharmonic, then it'll be in this guy. And so this is, if m is bigger than p, then this is going to be better than this condition, which always holds because of the p monotonicity. So this is what. So forget everything on this slide, but this one thing here. F plus f twiddle is p twiddle. Why do I want to do that? Because if you take, it's because of comparison. Because if you have two different, if you have a harmonic, then remember v, and then minus v is in here. And if you have another harmonic u, it's f subharmonic. And so the sum being m little subharmonic, if you have the maximum principal here, then you're going to get that u minus b less than or equal to 0 on the boundary implies u less than or equal to b on the inside. And that's what you want for uniqueness in the gear show. So I mean, there's more going on, but that's the simple algebra part of it, which I didn't have enough slides. I got 50 minutes. So here's the plate problem, and it turns out to have sort of what I call a clean answer too, meaning you don't have to put any conditions on F in order to have a theorem. So some short of time, this is just a standard Dirichlet problem. You can read what it is. And uniqueness is where there's most one. So the comparison always holds. Here it is. Always. Yeah. Comparison always holds. And as I just outlined, comparison implies uniqueness. That was this argument with the U and the minus B. And you can need condition on the boundary, but sometimes if you have a ball that's going to be a good guy, well, maybe if a ball is a good, strictly convex in the classical context, it's a good guy for any other place. And then you not only have existence, but the Perron function, which is the is this regularization of the soup of all the subharmonics that on the boundary lie below the boundary function. That Perron function is actually is a solution. And no assumptions except for this one positivity condition. So there are two proofs of the hard part of comparison. For the existence, this was already completed for this case. That's the one I mentioned. This is where it's a classical case. And remember, here's the date. Bremer in 59, and then Walsh in 69 completed it. So the new part for us was to, in this existence half, was just to adapt your methods to this general case. And also the boundary convexity in general, we had to make sense out of that. Everything sort of knew what it was here in this classical case. Now for comparison, we have two proofs. So the original one in 2008 used the lemma Sladowski of several complex variables concerned convex functions, quasi-convex approximation, and the sub-affine functions enter in. And then a second proof, we didn't really know viscosity theory. So some of what we had reinventing the wheel, but maybe we have a little bit different wheel. So here's the theorem that's based on the more traditional viscosity theory. And this relies on a lemma of Jensen. So we found it slightly interesting that Sladowski and Jensen, Sladowski seemed to, nobody knew about him in this viscosity world, but it was 4 years earlier than Jensen. Running out of time. It turns out that these two lemmas, I'll say more, since it's not our time, I was going to say later on a different slide, I'll just say here. These two lemmas, which I haven't even stated, they're actually equivalent. They look different, but the hypotheses are one holds if and only if the other hypothesis holds, and there's a set in the conclusion, and the sets in the conclusion are actually equal. But the proofs are different. So let's see. So I've got just a minute to talk about something that's not constant coefficients. So I guess I'll focus on this, and last one I won't have time. So, given the sub-equation F, restriction makes sense. If I talk about first order, then everybody would know how to restrict because it's a condition on the exterior derivative of the function. So you know how to restrict the exterior derivatives. But two jets you can also restrict because there's you have to say it precisely with exact sequence using the quadratic forms or But anyway, what it amounts to is you can restrict one forms and you can restrict quadratic forms. So you put them together and you can restrict any full derivative or two-jet. So that always makes sense. And so you can just look at these. So this F now is a closed subset of the no, I'm still doing constant coefficients here. So F is constant coefficient, just restricting of quadratic forms. Tells you what your restricted subequation should be. And this geometric case is just where the restricted subequation is again geometric. It's just take the good planes that lie in the restricted plane. And so a special case of this theorem was this thing we did earlier. If you take a strip P subharmonic, and it's the same as the kind of arrow going this way.
By restricting to line.
I'm sorry?
By restricting to line.
Yeah, by restricting the line. But the arrow going that way, you can restrict anything. You get the F and O here. Yeah, so I'll finish with this. So Blaine probably remembers better than I do. I think we sort of had a proof of this, and we didn't know it was a conjecture. So we're on an almost complex. So this was interesting in the sense that we started with several complex variables, where there was this great tradition of studying version of functions. We actually ended up with a result in several complex variables. It was new. So, but on an almost complex manifold. So now, on an almost complex manifold, we have three definitions of query subharmonic, and they agree when U is smooth. So there's the distributional definition, and it's not this is really not a geometric case, unless you have a metric, and it turns out you cannot assume that you have a Parisian metric. You get a different answer then. Is that right, Blaine? You get a different answer.
If you take the Riemannian S.
Yeah. So it's not a geometric case. It actually is a subequation that's, you have to really consider the two-jet bundle, and what do I mean, not a geometric case? It's a convex, the F involved here is a convex cone subequation, meaning at any point, the fiber in the two-jet bundle is a convex cone with a vertex at the origin. And so to see if it was a geometric case, you'd want to take the polar cone in the lower two jets, and you want it to be generated at its extreme points, be somehow generated by the Grossmanian. So that's not the case here. But nevertheless, it's a convex cone, so it's going to be the intersection of half spaces, where these half spaces are linear inequalities, meaning linear, second order linear equations where you write an inequality. Well, and so once you have that feature, you can talk about a distributional subharmonic. And the classical definition on an almost complex manifold, I guess it depends on what you think it is, but here we just took it as means that when you restrict to the pseudo-holomorphic curves, you get subharmonics, which makes sense conformally. So no metric, all this makes sense. And the feature is that there's a theorem of Wolf and Nirenhouse that plenty of almost complex curves to any point. So there are plenty of not higher dimensional almost complex submanifolds, but curves. You have an abundance of curves. And so that's the classical. And then the definition using an F, I haven't told you what the F is, you have to work out what the F is, but you just use smooth functions, and the F has to be whatever you get inside of here when you take two jets of smooth functions that satisfy one of these definitions. So that's the indirect description of depth. So the hard part here, so I guess we sort of already, yeah, we kind of had this proved.
Are they all equivalent?
They're all equivalent. I forgot to say that. Thank you. Yeah, they're all equivalent. And so we were sort of trying to be in this viscosity world, so we do this, but we really weren't focused on it down here in the viscosity world. So we heard about this Pauli conjecture and these two are the same. We knew our restriction theorem, see, is what says these two. Says that you have subharmonic. If you're pluri-subharmonic down here, then you're pluri-subharmonic in classic. So this is Millman principle, is the thing that they give you this fact about convex heads, the intersection. Well, thanks a lot.
Thanks, Reese. Other questions? Yes.
So the questions. This B operator that you started with, where you construct B with the gradient of B. You said that if B was not parallel, you have to modify that.
You said, what is the modification?
Yeah, how do you modify this group?
Let's see. Blaine probably know what it is. Where's the answer? There's a,
It's track of the coffee.
what? I forgot. It's a, sorry.
This is issues of Riemannian Hessian.
Oh.
With 1 point, just look at the Riemannian Hessian and the restriction of that. It's when you keep playing.
Yeah.
When,
Yeah, on the G.
yeah.
Remember, this is from the very first line of the slide with all those papers. wait. Yeah, well, I used the eraser a little bit when we decided that calibrations weren't enrolled in my head. I can tell you what happened.
So that goes to my second question. You said that since a lot of these results didn't have anything to do with calibration, but what if you would be interested in these things in specific pieces of calibration?
Well, all these theorems hold. The Dirichlet problem.
For example, in G2 case, or in Calabrian case, generalizing these equations, so, how you say it, do you get any insight in geometries out of these financial equations?
Well, see, the original, yeah, I think if you, I think this is the point. Originally, we were studying the calibrations and we looked at the geometric side, the submanifolds that are cycles. So now we're looking at the analytical side, and so now you have to be happy with analytical things, these pluri-subharmonic functions. So if you know several complex variables, they do play an important role, but geometrically, we've already sort of did our best geometrically, and now we're moving on to the, I don't know.
Any other questions?
Well, I have a comment.
Yeah.
This is 20 years in this apartment in Paris, where the guy in the 30s was there, George Valley Long, and in the 50s was Pierre Lalong. When I moved in, there were these old, dusty papers where Lalong had introduced the definitions of subharmonic functions from 41 and 42. I could probably locate those things.
It's probably also an oak. It's probably an oak earlier. I don't really know
Yeah,
history
they
very
made
well,
that.
but he certainly Long has a beautiful little book.
The law?
Has a nice little skinny book
Yeah.
on the subject. And he,
Oka.
no, Long. Oka, that's sort of been, I've never heard anybody that claimed to, that's alive now, that claimed to have read his papers, but I'm just guessing it's probably in there.
Any other comments or questions? If not, let's thank Reese again.